Welcome everyone to the latest in the Net Zero Industries webinar series. Today our topic is Carbon Shift, Redefining Industry Through CCUS. I'll actually give an introduction to our agenda later, but first, if I could please, I'd like to welcome Urban Paeta, who is the Mission Director for the Net Zero Industries mission, and to please give an introduction to Net Zero Industries and our webinar program. Urban, please.
Yeah, hello everyone. Thanks, Alan. Thanks for the introduction. It's my great pleasure to welcome you to today's webinar. It's part of the Net Zero Industry Insight series, as Alan already had pointed out. And this is already the 6th webinar in the series, and it's a particularly special one, as we are delighted today to co-host it with the Clean Energy Transition Partnership. Over the past years, they have done outstanding work in funding crucial transnational projects that support various dimensions of the energy transitions. So I'm really grateful that we can do that together today. Thank you all for joining from across the globe. So good morning, good afternoon, and good evening. We are really delighted to have you here. Today's topic, carbon shift, redefining industry through CCUS. Carbon capture, utilization and storage represents a key technological pathway for decarbonizing hard-to-abate industries. Nevertheless, CCUS is among the more challenging and probably challenged ones when it comes to technological readiness, societal acceptance, and when it comes to viable business models for future value chains. And to address this complex nexus of challenges, we need trust, and trust in new technologies that can open the door to entirely new opportunities for cooperation, innovation, and value creation. And this aligns perfectly well with the very founding idea of the Net Zero Industries mission. And if you want to move to the next slide, I think you have an overview of our goals. Yes, there you can see a wrap up of what we are and what the challenges we address. So we are a global initiative under Mission Innovation, and we are committed to accelerating the transition of energy intensive industries such as cement, steel, and chemicals, and we want to help them to reach net zero emissions. These sectors are not only central to many of our economies, but they also account for around a quarter of global greenhouse gas emissions, and transforming them is obviously essential if we want to achieve our climate goals. Emissions from these industries are particularly difficult and very costly to mitigate, and many technologies still need to be scaled up and made commercially viable. That is why our core objective is to build trust, as I said at the beginning, in these new solutions. And if we move to the next slide, you see our mission goals. Our goal is to implement 50 large-scale demonstration projects across the mentioned energy-intensive sectors, using all the available technological pathways, which is a variety. And we support the fast-track development of breakthrough low-emission technologies, aiming to move to higher technology readiness levels, and that will eventually help us to reduce capital expenditure. And what to expect today? We will explore today the latest developments in CCUS. We will highlight cutting-edge technologies and best practices from the industry. And we hope you leave with valuable insights into how we can collectively leverage CCUS to reach net zero goals. Trust is fundamental to this effort, but so is funding, and that is why we are especially pleased to be joined by our colleagues from the Clean Energy Transition Partnership, who will present current and future funding opportunities for future CCUS projects. As we used to say, the journey to net zero is one that we need to make together, and it thrives on the open exchange of knowledge. And as always, we encourage you to actively participate in today's session. Please ask questions, share your thoughts, engage with fellow attendees. And thank you once again for being here. Let's get started. I'm really looking forward to the presentations. And with that, I'd like to hand over to Alan again, Alan Monaghan, who will guide us through today's webinar in his role as our mission coordinator. Thanks.
Thank you, Urban. a quick rundown, as you can see, for the agenda. We'll be getting a presentation, a keynote presentation on the role of CCUS in industrial transformation. Shortly afterwards, we'll be getting a presentation on the CETPartnership and the joint call for 2025. After that, we'll be looking at the projects. We'll be looking at the Greensmith program for low carbon steel production, a project on biogenic CO2 involving the chemical living combustion technology for biomasses, and then our last presentation will be CC upscaling the international demonstration scale implementation and cross-border coordination for RHI Magnesita. The format for all of our presentations today are 15 minutes of presentation, hopefully leaving time for 5 minutes of questions. I'll invite all of our audience, please, to put your questions into the chat, identifying which speaker you'd actually like to address it to. That comes in very useful later on in case we don't have time in that 5 minutes after their presentation, because we do have time at the end of the session to hopefully wrap round and ask questions of our speakers that we did not get time to in each one of these speaking slots. So again, please, questions into the chat, identifying which speaker it is for. We will try to get through as many of your questions as possible. We are recording the session today, and it will become available in the very near future on our YouTube site and our website. And the presentations that are given by our presenters will hopefully be created in a PDF format for you to be able to see again on our website before too long. Without further ado, I'd like to introduce, please, our keynote speaker, Professor Peter Steiding. Now, Peter has a background in chemistry and is a chartered engineer specialising in carbon capture and catalysis-based technologies. Peter is also the co-founder and director of the award-winning carbon capture company CCU International. Please welcome Peter, if you could share your slides.
Good morning. Thank you for the introduction. And I believe the slides are being shared for me because at the moment I'm at the Chem UK conference.
Absolutely. Thanks, Irmgard, if you could. One second while we key those up. Excellent. Thank you.
Excellent. Right. Yeah. So thank you for the chance to give this presentation. We're at a key point in the role of CCUS in transformations. If we could go to the next slide, please. Okay, so if I look at this from a UK perspective, I've been in this game for quite a while now, and we haven't really progressed much since about 2008 when I really started getting involved. If you look at the quote from Hansard, we've had 3 failed projects and things have not really got going. And Sarah Jones, the minister responsible for looking at CCS, put out this comment, which is unbelievable, that she believes CCUS is an emerging technology. The patent for amine capture is nearly 100 years old. This is not emerging technology, but this is something we really need to address now. There are projects ongoing in the UK, but still nothing has been delivered at scale. I want to give an example of a project we've been working on where we've delivered at a scale, but we want to go bigger. So next slide, please. So this all started, right, so yeah, that's the one. So back in 2017, I co-chaired a panel at Mission Innovation on CCUS, where the term CCUS was really put forward as the driving force. It was held in Houston, Texas, driven by Barack Obama and Bill Gates. It was the G20 nations with the EU as a bloc. And we put out this report through the DOE in May 2018. And it had a 5-year plan, which unfortunately lots of things got in the way, such as elections and COVID and various other things. But below that, you can see a figure that was proposed by myself and Rebecca Boudreau at that meeting. And that was to take renewable energy and CO2 and convert it into value-added products. And that was ranging from polymers through chemical intermediates, alternative fuels and energy storage, advanced materials, including aggregates and cement, and then a really long-sighted vision, which was pharmaceuticals, healthcare, and consumer products. And one of the ones under chemical intermediates that we really brought up for the first time was surfactants. These are materials that go into cleaning products and home care products. And this is the first time it was really brought up. As you'll see from the example I'll give, that has now become a reality. Right, next slide, please. This is a paper that we published relatively recently, a couple of years ago, in Joule, which has an impact factor of 46. This is a lot of the experts from around Europe working on CCU, carbon dioxide utilization, because at that time there were a lot of myths flying around that it wasn't a profitable business to be involved in, that CCU wouldn't work. And this was a myth-busting paper headed by Jan Mertens from Angers in France. And it really, for the first time, spelled out what could be achieved using CCU. Next slide, please. Back in 2016, the Global CO2 Initiative in Michigan put out this document which was written by McKinsey & Co., which showed the potential reductions in CO2 emissions, so the mitigation potential, and that's in blue, and the potential revenue, annual revenue that could be achieved if we did carbon dioxide utilization. The light colors on the blue and the green are business as usual. What happens if we don't really push this forward? And the darker colors are what happens if we push the envelope. We try and promote this through incentives, through government push and industry pull. And this was estimated to be a $1.1 trillion per annum market by 2030. That's now been revised, and it's probably about $3 trillion US dollars. So this is actively going on around the world at the moment, but still not at the scale we want it to be. The scale that we're at the moment is still higher than carbon capture and storage. And I fully acknowledge we need carbon capture and storage, but we also need utilization, because while storage is a waste management problem, which will involve cost to business, CCU utilization generates income through value added products. Next slide, please. I just want to go quickly into what we really need to think about now. This is a theory that was put forward by Peter Thiel back in 2014. And this is how do we build new technologies? So there are on the x-axis, you've got globalization, which is you have a potential product and you grow it up to a value N. I think something's missing there, and that should be the N should be time dependent. So it should be dN by dt. How do you get there at speed? On the y-axis is technology, and that's the 0 to 1. You start off with something which is conceptual, that's in your mind, and then you go to 1, which is the starting point for any business. So 1, you've established yourself, and then you can start looking at the globalization, which is the growth. Next slide, please. And that's really where we need to look at now. So I want to give one specific example. This is a project I've been involved in called Flue to Chem, where we're taking flue gas from, initially it was from the steel industry, but as you may realize, UK steel industry has had a few problems recently, but we're also taking it from paper mills. So you'll see on there, you've got Holmen Iggesund, which is a Swedish company, and UPM Biofor, which is a Finnish company with operations in the UK. And we took emissions from those two factories, from the biomass conversion units, and looked to convert them into surfactants that could be used in home care products. Next slide, please. Why are we doing this? Well, if we look at industry, chemicals industry, we have a predicted growth of around 2%, 2.5% per annum. which means if we take the 2020 value and project it to 2050, where we're expecting net zero, we're looking at 5.5 billion tons of chemical products being produced. Now, at the moment, most of these are from fossil-based sources, as you can see from the black bar. But because we're going to net zero, we have to diversify and take those from CO2-based products, recycled carbon products, and also bio-based carbon products. And the problem is that as the oil dependency is decreased, that 5% of the barrel that goes towards chemicals could easily be lost if we don't intervene now. Next slide, please. So why did Flutichem come about? It was a long transition. It took 3 years to establish, and we were given 2 years to deliver a new industry. We realized that net zero will not be achieved unless we look for another source of carbon. Carbon dioxide is one of the main contributors to global warming, and therefore, if we can use CO2 at the right scale and the right cost, we have a feedstock which is readily available. The consumer market has the most immediate driver for change. So there has to be a social impact to this as well. But we also, as well as CO2, we need to look at other feedstocks of carbon, and these include plastics, paints. These, the list is endless, and that's just on the carbon side. We also need to look at recycling other fossil-based products, such as calcium oxide, making calcium carbonate. Instead of looking to extract more calcium carbonate from the environment, can we produce that from waste stocks that we generate during the processes? Next slide, please. I'm not going to go into too much detail about this. This will be on the slides as they're circulated. But why did we look at surfactants? Well, there is a huge market for surfactants, and particularly alkoxylated surfactants. So these are things like alkyl ethylene oxides. We want CO2 to be part of the value chain as a source from emissions. We want to convert it into hydrocarbons, to ethylene oxide, and manufacture the alkylated surfactants as we do the capture. This is a unique project because we brought 17 partners together, most of which are competitors. So you'll see there Unilever, who led, are together with Procter & Gamble from Reckitt Benckiser and Croda. So these are usually competitors, but now we're working as a team. It was a £4.4 million project, of which 2.7 was grant funded, the rest being industrial leverage. Next slide, please. And the idea was to take these foundation industries, so Holman, UPM, Tata Steel, and move forward to capture it using technology from the University of Sheffield, which has now been, it's now patent pending and licensed to CCU International. Carbon Clean weren't able to do any of the capture because of prevailing legislative issues, which is a huge problem. But then Sheffield, Johnson Matthey, BASF, LanzaTech, all making materials that would go into the final product, Croda producing the surfactants, and then the fast-moving consumer goods companies making the products, which we're going to announce in June in the Houses of Parliament. Next slide, please. This is just to show the commercialization is a long journey. The capture unit, the Flurifin system, is a pressure swing adsorption system. We started it in 2011. It's only recently started to go to capitalization. It's gone through a long history of development before we can introduce it to the market. But now, as we said, it's won awards. So the engineer, Collaborate to Innovate, and recently the iChemE Global Award for Startup Company of the Year. But how has that affected what we've done in Flutichem? If we go to the next slide, please. This is the plant up at UPM Caledonian Paper Mill in Scotland. And you can see me and a co-worker on the unit on the right-hand side, you can see the biomass combustion unit, and you can see that little green box at the bottom, which is capturing up to 1 ton a day of CO2. If you hit the button, we should be able to expand on that. Can you do next slide, please? Yeah, so there you see the unit sat by the combustion house. So it's a small footprint. It's a highly efficient system. Next slide, please. And what do we do with the CO2 that we capture? Well, we convert it into surfactants. And in this case, the byproduct is also synthetic diesel, which you can use to power an engine. So we're starting to do it at scale. We now need to go to bigger scale. And part of the issue is the regulations surrounding use of the different systems on existing power plants, because you have to go through a change of use protocol. Next slide, please. So to conclude, what have we learned so far from the Flue2Chem project in terms of how we go to industrial defossilization? How do we go towards net zero? The first thing we realize is we are going to need a lot of green hydrogen, not blue hydrogen, not black hydrogen, but green hydrogen. There is a possibility that we might be able to use white hydrogen or gold hydrogen, so geological hydrogen, but we need hydrogen. Getting things to the right place is a challenge. We have to get things onto a site, and putting something new onto a site is full of regulatory problems. We couldn't make that synthetic diesel on site because it would have taken 2 years to get the permits through to do that, by which time the project would have finished. Biology can make you dodecanol, can't make you dodecanol, which is what we need. Thermocatalysis can, but it can't make a lot of it. The UK in particular is missing a lot of necessary scale-up facilities. That's not necessarily true in Europe, but something needs to be done on a European-wide scale. Planning is good, but nothing can compete with engineers on site. You can do all the models you like, but you need someone with a spanner and a hammer to actually get the thing working. And regulation and fiscal policy needs to be better aligned with net zero goals. And this should not be seen as a mitigation technique. It will help mitigation, but it should be seen as an enabling technology to allow the chemicals industry to survive in a net zero future. And with that, I'll say thank you and happy to take questions.
Excellent. Thank you so much for that, Peter. I'll take the moderator's prerogative and ask the first question. Why do you think it's actually taken so long for carbon capture solutions to actually become real and established in industry?
So as I said, the patent dates back to 1930. So what have we done since 1930? That was the 0 to 1 on that graph. It's now the N by dt. What's happened since then? And the problem is we've just, I'm speaking now from a UK perspective. From the UK, we've invested in the same technology over and over again. So there's the old adage, you know, the definition of insanity is doing the same thing over and over again and expecting a different result. That wasn't Einstein, that was Narcotics Anonymous. We're doing the same thing. And I did a radio program a few years ago and said we've not changed what we're doing. We look at the current things and we're still using amine technologies. And amine technologies have not reached the high end value that we expected. So we need to look, I hate to use the word disruptive technologies, but we need to look at step change technologies, technologies that will give us a different approach, which will bring down the cost of CO2, bring down the complexity of the plant, reduce capex, reduce opex, and reduce the land use. I hope that answers the question.
It does. Thank you. We have one question there in the chat. Pardon me. It's from, sorry, I can't make it. Sri Ramda. I would like to see, I would like to ask about LCV, HCV, or the syndiesel from the samples you got. How is it different from the original syngas diesel?
So what we do in our process is we use a modified catalyst. It's a one-step process. We don't use syngas, so we use CO2, and it's CO2 directly to the hydrocarbon. So it's a very bespoke catalyst, which will give us a very narrow product distribution. So syngas tends to give you a wide distribution, including, well, depending on which catalyst you use and the pressure and the temperature, gives you light fractions, mid fractions, and also waxes that you then need to hydrocrack back. Ours gives us a very narrow distribution from about C7 to about C20. So we're starting off with a much cleaner fraction, and then we do the fractional distillation to take off the surfactant fraction, which is C12, which is also what is needed for kerosene, but not exactly the same as kerosene. But we can separate out the C8, the high octane stuff. We can separate out the high cetane stuff. So it's actually, I would say, cleaner than the diesel you get from the usual Fischer-Tropsch process using syngas.
Excellent, thank you. I'll ask another question if I could. A lot of the work I've seen in CCU over the years has been calcium carbonate. You've obviously targeted consumable and hopefully profitable products. How much of a challenge was that, and what kind of guidance could you actually give to others to actually focus on that value proposition from the products rather than just purely the purpose of capturing carbon?
So what you have to remember is technology like Fischer-Tropsch or modified Fischer-Tropsch is not selective. So you get lots of byproducts. And if you do a life cycle assessment or a techno-economic analysis on just that middle fraction that gives you the surfactant, it can be said there's no added value because it's such a small amount. But there's high value for the diesel, there's high value for the gasoline. But what you need to look at, it's a whole system approach. It's not just that. So you mentioned calcium carbonate. One of the byproducts of the combustion is fly ash, and the fly ash is rich in calcium oxides. So what we're also doing is we're taking the fly ash and reacting it with the CO2 to give calcium carbonate, because then you start to build up a circular economy. So if you look at someone like UPM, they use calcium carbonate to make the paper as a binder and also as a finishing agent. When they take the waste wood and they combust it, they produce the fly ash, which contains calcium. We can then extract that calcium using the carbon dioxide and make precipitated calcium carbonate that can go into the process. So you need to look at the whole system. You need to look at where the value is, and also remember that if you're doing just CCS, which as I said, we need to do, but if just CCS, you're going to have to pay to landfill that. And when I say landfill, I mean underground geological storage. It's the same way. There's a company called Carbonate who make calcium carbonate, and they take air pollution control residues, which are toxic. They then take a gate fee for that. They react it with carbon dioxide, and they make building materials in which the toxicity is reduced through encapsulation. So it is about looking at the whole supply chain, but it's also about bringing the cost down of the products that or the co-reactants. So hydrogen, bring down the cost of carbon dioxide, be careful about water use, for example. So do look at the whole system, not just the immediate focus.
Excellent. Thank you, Peter. There's still questions coming through, but if we can hang around and if you can stay on the call, please, Peter, we'll actually have questions at the end. But for our timing, we're going to move on now. It's my pleasure to please introduce our next two speakers presenting on the topic of the CETP program. And that is Dr. Hannele Holtinen and Dr. Orge Stangeland. if I can, please, Hannele is the RD and I lead of energy systems at the CLIC Innovation Program working at CETPartnership, the TRI6 Office for the focus of integrated industrial energy systems, and Orge is a special advisor at the Research Council of Norway, where he is responsible for the Research Council's activities within the CO2 capture, utilisation and storage space. It's a pleasure to have you both with us today. If I could hand over. Thank you.
Thank you, Alan. So I think I will start. So I could first introduce the Clean Energy Transition Partnership. So we have co-funding from the European Union, but the main funding comes from the member state national funding institutes. And we, of course, aim to contribute to the EU goal of climate neutrality. And we have annual calls for research and innovation. In addition, since we are a partnership, we also have activities for the knowledge community, peer-to-peer events, and also the impact network to boost impact maximizing. So the next slide will show in the map that we are covering Europe, but also some funders outside of Europe, and mission innovation funders are also joining and can join our yearly calls. So depending on the call and the topic, we sometimes also see other funders coming. And indeed, it's 50 plus funding partners, and then coordinated by different subset of these funding partners. And also this collaboration with mission innovation is of course very dear to us. We have had two calls where the projects have already started. So we have 100 plus projects already working, and then currently we are at the final stage of giving green light to a third set of projects and opening a call, the next call in October. So I think next, Åge, you could tell us a little bit about the focus area on CCUS.
Yes, thank you, Hannele. The CTP is divided in 7 different thematic initiatives, and many of them are on renewable energy, but today we will focus on those relevant for CCUS. And our transition research initiative number 3 is targeting CCUS, hydrogen and renewable fuels. And we aim at global decarbonisation by accelerating the development and implementation of CCUS by supporting targeted research and innovation projects. And key objectives is to reduce cost and implement CCUS at industrial scale. So back to you, Hannele, to say more about TRI number 6.
Yes, our focus area on integrated industrial energy systems is actually a new focus area. Many of our focus areas are building on the previous ERANET funding schemes, but this is a new emerging, very important area of research targeting decarbonisation of industry. So we are looking at projects that would develop and demonstrate technical solutions enabling efficient carbon neutral industrial production sites. So industrial power heating and cooling, and also hope that they have impact for scaling up, since we know we have urgency in getting our industry decarbonized. And next, I think we have an example. We are showing you an example of our knowledge community and impact maximizing event. So we had 2 events together with our 2 focus areas on industrial systems and CCUS. And we invited first Northern European and Central European industries to a 3-hour online event workshop, and then we had another event for the Southern European industry, and then from these two events we made these summaries. We had two sessions. We were first looking at the research and the development and innovation needs, and then the sort of operational environment and market shaping. So Olga, would you like to tell a little bit more about the summary of the RDI needs, please?
Yes, this slide lists the research needs that we see, and within carbon capture, the main objective will be to reduce the cost for the carbon capture process and obtain high capture rates, capture up to close to 100% of the CO2. And upscaling will also be a challenge that we need to address. And we also see that material science is important to develop new materials that can make the capture process more efficient. Bio-CCS, also an interesting topic that need more research. And moving on to 2030, direct air capture will be a very important technology to further develop. Furthermore, for the CCUS process with focus on the utilization, there's a need to bring down cost and also to ensure high energy efficiency for all parts of the utilization process, and also prepare for upscaling. If we move on to CO2 logistics, we all know that it's important to link CO2 sources and CO2 sinks, and we could need a CO2 atlas where industrial hubs can be planned, linking efficiently the sources and sinks of CO2. And also on 2030 onwards, we need to develop an European CO2 pipeline network. And then moving on to CO2 storage, there are also R&D needs that is related to reservoir integrity, that's for sure, to make sure we can store the CO2 safely. We need more research on drill hole technology and integrity. And we also need to develop efficient monitoring technology so that we can make sure CO2 stays where it's supposed to be and monitor where it will be moving when it has been stored. We can move on to the next slide where we have R&D needs within other topics. We need to develop business models, and Peter was touching upon this as well. At the moment, capturing and storing CO2 is at a high cost. We need to figure out how we can establish business models that make this flow within industry. We need to develop standards. When we transport CO2, we need to have a good control of impurities and the quality of the CO2 stream. So we need to research that more. And also environmental impact will be important. We need good life cycle assessments and we need sustainability. And this should be part of all kinds of research activities. And furthermore, the cross-cutting topics will also be very important. And one thing coming up on cross-cutting is artificial intelligence. That is a new technology that could be very helpful, both within capture, utilization, transport, and storage of CO2. And also on cross-cutting, we need capacity building. There's a need for labor requirements. We need to educate future experts. So it's in general quite wide aspects that we need to focus on, from capture to utilization and storage, and also the cross-cutting and business models. So we are moving into the market shaping, and Hannele, I leave it to you to describe the needs.
Yes, so indeed. So from these R&D needs, we continued with our stakeholders to look at the operational environment and the barriers, and what are the things that we could do together as a technology to improve the operational environment, so-called market shaping activities. So for the technology itself, for CCUS, we felt that there is still need to understand better the industry needs. So really bringing industry and the authorities together for better understanding, and this would pave the way also for a lot of the regulatory work that is still needed for this new technology to be applied more widely. So regulatory framework issues, there were several that were identified also for the technology and also for the other like cross-border exchange of CO2 and the other topics as well. And then we also did some preliminary identification. Okay, with whom could we join forces to bring forward these issues? For the logistics, of course, it's about CO2 infrastructure, but also about standards and specifications for the transport of CO2. In the next slide, there are also then some other needs and topics that were identified for storage, and then for business models, value chains, also highlighting the importance of industry symbiosis, setting targets, having long-term transparent framework for incentives, and then also working on these value chains and boosting the development of CCU, especially was seen very important. And then finally, in our last slide, we brought up also standards, knowledge sharing, social acceptance and environmental impact, where there are things that could be done and ideas of sort of how to do that with recommendations and creating different certificates, for example, communicating best practices, and also sharing information of all the environmental impact work that is done. So this was just summarizing something that we get out of the events that we organize under CETPartnership. And then next, we would still like to highlight that there is a joint call opening soon. So we have the call launch in a week, but it's already available in our website. Link will come later in the slides. And for the industrial energy systems, we have a call module 8, where we target reducing emissions from industrial processes and also taking the system approach. So how to integrate the industrial systems in the wider energy system, especially possibilities for flexibility, which will also enable better use of renewable energy in future. So the main industries we target are food and drink, cement, pulp and paper, steel and chemicals. And we have listed here example topics of efficiency, circularity, electrification, and also then green hydrogen, CCU, and bio-CCU, especially. And reduction of emissions, so mainly CO2, but also others. And then with the flexibility offered for energy systems, we also hope that all this will accelerate industrial decarbonisation in future. So, Åge, what about your core module for CCU technology?
Yes. I didn't include a slide for my core modules, but we have 2 core modules that are quite generic on CCUS, developing new technology, also addressing the cross-cutting issues that I mentioned. And we have 1 core module on hydrogen and renewable fuels that is also targeting technology development and the cross-cutting issues. So overall, the core has several core modules, so it will be important for all applicants to look carefully into each of them so that you can figure out which is the right one for you. So I will be moving on to this slide that shows the impact from international R&D projects. This can be useful for all of you so that you know what we are looking out for. And we would like to see added value from the international collaboration. And the added value we have experienced so far in ongoing projects is that we see that we can have larger projects when several countries join forces and put money on the table, and then we can have partners from many countries. Project grows bigger, and the bigger projects will have bigger impact, not only on the national scene but also on the international scene. We also see that the CTP calls leads to strong and well-functioning R&D and innovation collaboration across borders. And also we see that in ongoing projects, there's a strong relation between academia and industry, which is highly appreciated from our side. We also see that international cooperation already in the research phase will increase the chances for transnational large-scale implementation of CCUS later on. And we also believe that results coming out of the CTP projects are relevant for the European Strategic Energy Plan and also for mission innovation. And we also see that the CTP projects has a considerable potential for communicating and disseminating key results beyond the scientific community. So this is the impacts that we see, and we hope that new projects will contribute to this. And this is back to you again, Hannele. We are close to the end of our presentation.
That's right. It's just to let you know that we are organizing a matchmaking pitch event. So we have the Beat2Match platform for finding partners. But if you have an idea and you want to make a pitch, whether you're a researcher or industry looking for transnational partners, then this is for you. And then we have a list of our events on the next slide, just showing that regarding the call. We have the call launch webinar, and we are specifically describing our call modules related to industrial energy systems and CCU and hydrogen, 13th of June. And then is this matchmaking event also. Here you have links. And then CCUS is organizing this knowledge sharing workshop in the fall. And
Thank you, Hannele.
This was all we had.
Yes, that was all from our side. And sorry, Alan, for stealing a bit extra time here, but back to you. Thank you very much.
That's fine. That just eats slightly into the available questions time we have. And that's a prompt. Just please, if you have questions in the chat, if you could make them quite concise and clear, and identify which speaker you would actually like to answer that question in case those questions get delayed until the end of our sessions. But I do have one question for you. I'm not sure which of you would prefer to answer. Collaboration is essential. We all know that. And I think the work of the CETP in driving that collaboration is absolutely commendable. But if new countries want to join the CETP, what do they have to do? How do they actually become members?
Yeah, we would like to see new members joining CTP, and if there are some countries that would like to join, they are welcome to do so. And what they have to do is to come up with money for upcoming CTP calls, and if they have money available, we will include them in upcoming calls. It's as easy as that.
Excellent. I often draw the analogy, whether it be collaboration for research, collaboration on funding calls, or even just collaboration in knowledge sharing. It's like the tradition of a bring a plate dinner. If you're willing to bring something to the party, you're going to actually get a lot more back in return. So the small contributions that more people make actually deliver so much more in compounding the amount of benefits that come back. I do notice, if it's a very quick one to answer, there's a question I noticed in one of the commentaries that was made, and it said that they believe there were barriers because of the need for high purity in production in CCUS. Is there any quick comment you'd be able to make about whether or not these high purity constraints are really necessary?
That's a tricky one. That is being discussed among industry, researchers and regulators. The need for purity on the CO2 stream. And there are research ongoing to develop reasonable limits for impurities. And if you put that too hard, it will increase cost and make it difficult to obtain a very clean CO2. But on the other hand, if you do not have a good control of impurities, you can end up with corrosion in pipelines, or you can get solid materials precipitated, and that could clog the pipeline and block the flow. So this is an ongoing topic. We need to research to find the right level of standards for the CO2 stream. So it goes two ways. We need to make sure we can have safe CO2 flow in pipelines or in ships or however you transport it, but we must not make it too strict and too costly.
Excellent. Thank you both for that wonderful presentation. It is now up to me to move on to our next speaker. I'd like to please introduce Leonie Looking. Leonie is a scientist at the TNO, a Dutch research organisation, where she focuses on absorption-based carbon capture technology. Furthermore, she's the project coordinator of the Greensmith project, which she will be introducing in this webinar. We are honoured to have you with us today, Leonie. If you could share your slides, please.
Yes, thank you very much for the introduction. 1 second. There we go. I think you can see it now. Yeah, so I'm happy to present our project, the Greensmith project, which looks at general low carbon steel production. So I think most are already aware, but basically why CCS and CCU important in the iron and steel sector. And in generally, when looking at any of the scenarios, there will always be a need for CCS in order to get to the net zero that we desire. And the problematic part here is in the iron and steel industry, these are what's considered difficult to avoid emissions. So solutions there have to be found. And for this, generally what we see is there's a lot of emissions. And per ton of steel, we have on the European side about 1.7 to 1.9 tons of CO2. The idea is how to go forward in general for the steel industry is recycle more scrap. So that's already something that's being done. Improve the efficiency of the iron making. That requires changes to the steel production process, even whole new furnaces. Switching of reductants. I think the most commonly known now is switching to hydrogen direct reduction. And lastly, capturing CO2. And within the Greensmith projects, we aim to address the last three of these. Specifically looking at the capture of CO2 and permanent sequestration. We do this with what we call our stepwise technology, which is based on sorption-enhanced water gas shift. So in old terms, this would be called a pre-combustion technology. So it's a gas that still contains, so it's looking at gases that still contains CO and therefore energy and what to do with this. In building up our technology, because I think this is also a very interesting part, is about how do you actually get a carbon capture technology high in its TRI. And so we had low TRL projects along the line, but the most interesting ones, I think, are the higher TRL projects. So there in 10 years ago, we started the Stepwise project, which looked at can we capture CO2 from residual steel gases and what is the performance? And actually, to our joy, we were able to outperform what we thought we would be doing. So we had a low speccr, high cost advantage, and also a benefit of this technology compared to amine scrubbing is that it has better improvement on all LCA factors. So the material that's being used in this technology is basically a sort of clay. So it is leading to very little environmental impact, which is a massive benefit if you're looking at large-scale implementation. Following of this project, we looked at various versions of how to implement that in different ways. So we had the Fresney project, where we looked at taking these off gases and turning them into methanol. The benefit of this is that we are reusing some of the CO2. The ratio is such that you will always have more CO2 than you can at least use with the hydrogen present in the gas. But you are, we were able to produce methanol from this. So all the way, we proved the production process to the point that we actually provided Stena Line with a certain amount of methanol, and they ran their ferry on this. So we really, the full production chain, and also here we could prove that there's a positive business case for using this, rather than the standard process, which is just burning these gases. In addition, we had the C4U project, where we looked at decarbonisation of the traditional steel mills. And we actually proved within a first-time demonstration that we could use decarbonised blast furnace gas to fuel the reheating furnaces. So in effect, decarbonising the later steps of steelmaking. Lastly, now we are currently in the stages of the Initiate project, where also in the shape in the form of CCU, we are looking at combining and doing industrial symbiosis between iron and steel sector and the ammonia and urea industries. What you can see on the images there is the erection of the reactor columns that is needed for our technology. Just give an insight into how this Initiate project works. It's basically by creating a symbiosis, we are able to use the off gases that has a favorable nitrogen CO content to our advantage to produce ammonia and then urea. This is because our technology converts CO with steam together to CO2 and hydrogen. It then separates the CO2, so we have a nitrogen-hydrogen mixture, which we then can convert into ammonia. And then lastly, in a step, we can actually convert it to urea for example, the agricultural industry. This process does still require sequestration because the urea process, again, doesn't need as much CO2 as the traditional steel mill produces. But some of the CO2 is actually utilized in the urea. We finished a business study to identify what the cost drivers are, and these are in the end we see these for a lot of our projects. First of all, what we see is that we have in general a net benefit of this business case. So as we were discussed in the first presentation, it needs to become a benefit for the company to actually do this in order to drive it, that it's not just a burden. What we also see is, you can see this with the green arrows, the uncertainties at this point for this business study are rather large. They're mostly on the side of the benefits, meaning we were assuming that there might be more benefits. But things like, for example, the CO2 storage are a large uncertainty. Partially, part of that is impurities in the CO2, transportation, etc. But we also see on the benefit side large uncertainties, often coming from policies, etc. But with this, I want to now talk about the Greensmith project. So the Greensmith project is part of the CETP. And within this project, we want to demonstrate how we can use the stepwise technology as part of the Greensmith integration to have hydrogen and CO recovery from different integrations of the plant. The idea behind this was that we won't have, we look at the progression of the steel industry and how it can build. So we have the traditional steel mills with blast furnace and basic oxygen furnace. And if on site you want to slowly move towards direct reduction, which has an improved efficiency, how can we integrate these to get the biggest benefit? For example, can we use the off gases for the direct reduction route as input into our blast furnaces? And can we use the outlets of the blast furnace as input for our direct reduction? So these were the thoughts with which we went in order to really reduce the need for carbon in the process, and so recycle as much as possible internally, and also capture to reduce the overall carbon footprint. The project itself started July last year. It's going until September next year. And our consortium, we always aim to cover the full value chain. So this means in our case, we have Acieri d'Italia involved, and as a standard traditional production route, and Stegra, formerly Hydrogen Green Steel, as one of the novel hydrogen DRP based steel manufacturers. We have technology suppliers involved. In this case, it is Kisuma who supplies the material for our technology, the sorbent that is needed inside our reaction columns, and Porworth involved as an EPC that's strong in the steel sector. And then lastly, we have two research organizations involved. That's from our side, TNO, as the developer of the technology, and Sverim, who are the Swedish steel research, or actually metal research institute that is closely connected, and it's also the location where we have our pilot plant that you saw in earlier slides. The project aims to actually address all the scales of the capture capacity to improve on all levels, to get the best results possible. So on the gram scale, we are looking at improving the sorbent material. So this is where heavily Kisuma is involved as a sorbent supplier. We are looking at composition, but also advanced shaping, with the idea that with shaping we can improve the performance dramatically due to changes in pressure drop, etc. On the kilogram scale, this is where we have on our site at TNO, we have a small version of our unit where we can do TRL 5 demonstration to showcase that actually these integrated production routes are possible, and showcase also the requirements when it comes to OPEX, etc., and to just demonstrate the possibility. On the kiloton scales, we're looking at doing a basic engineering design package to go towards a TRL 8. What we have seen is that a lot of the times it is difficult, the larger the plant gets, so the higher the TRL, it becomes more and more difficult to accurately assess what is needed. So when going into follow-up projects, etc., we do need to make an actual design of what this plant looks like when we're at the really large scale. While the design package for a TRL 8 is currently looking at only 50 kilotons. The idea is that it can be a sort of modular system, so improving we can increase the size simply through adding extra modules. But these, for example, it gives input into how can we roll out the technology, what is the requirement for on-site. So on permitting, etc. So we're trying to answer a lot of these questions there to really make the rollout as smooth as possible to go towards a first of a kind plant. And then finally, we have the larger scale, which is where we're trying to where we will do the techno-economics and the life cycle analysis for two sites. This is for the two end user sites, so Adi and Stegra, and with the idea that we always, in every step of the way, when we do our technology development, we always include these steps to make sure that any changes we do actually has an impact. So if we are talking about, for example, changing the shape of the sorbent, is the benefit significant for the cost, or are we, do we need to rethink this? Is this really worth it? Similar with the life cycle analysis. So this is one of the learnings that we apply to every project, that we need to have those elements involved there to prove to end users, etc., that it is a worthwhile technology. And with that, I'd like to thank you. Once again, they're our consortium members. I want to thank the CETP for this. And if you want more information, there is the website.
Excellent. Thank you, Leonie. I have at least one question in the chat. Please remember to add them in there. But I have a question I wanted to ask myself first. How long do you think that carbon capture is going to stay relevant for the steel industry? Or in the long run, will it shift to something when we move to a hydrogen-based steel production?
Yeah, very good question. I mean, on one hand, to do hydrogen production, we do need a lot of energy to produce the hydrogen. And the predictions, at least for the whole world, is not that everybody will switch over to hydrogen, DRP. But even if we do that, in order to produce steel, you do need carbon in there. So there will always be some carbon involved in the production of steel. So they will, in order to go to net zero, you will always need some sort of capture. So I still see it relevant to at least be able to separate out the CO2 from these processes.
Excellent, thank you. So a question from our chat. What is the capture technology used in the Greensmith project?
Sorry, yeah, I wasn't sure whether I was being clear. So this is our stepwise technology. Internally, we also call it CWEX. It's the Sorption Enhanced Water Gas Shift. So it is a pressure swing adsorption system that is able to operate at high temperature and high pressure to produce basically the clean gas. In our case, normally it's hydrogen-nitrogen mixture, and produce the CO2 at lower pressure.
Excellent. Now, another question from the chat, and I'm going to be reading it verbatim because I do not understand the science of it. Dear Ms. Looking, did you consider solid oxide electrolysis thermally coupled to metallurgical processes?
So more on the heat integration side, because, and please correct me if I'm wrong, this is about hydrogen production, solid oxide fuel cells, unless I'm off there. Not really. We do have projects in that range, but right now we're watching more on the really on this very basic process in order to not overcomplicate things.
Excellent. One other question we have here is, what is the advantage of this technology, the stepwise, compared to other capture technologies such as amines?
Yeah, I mean, as I tried to showcase in the LCAs, what we often see with amines, because they have degradation, for example, in the outlet gases, you have you still have amines present, but also generally amine solutions are post-combustion. So by that point, your gases no longer have energetic value, whereas by using our technology, where we are inside the process, we're able to recirculate the energetic gases and give it a higher benefit that way.
Excellent. So probably one last question before we head off. I don't know if it's a short answer or not, but there's obviously next steps in taking the technology further. What's the biggest bottleneck that you've got to overcome in scaling up and developing this technology?
In a way, it's funding, because what we see is that these installations, because they're addressing large emission sectors, they need to be big. And while there's interest from the industry, it is also involved a lot high risk in there. And in order to overcome this, basically we need good funding opportunities. There are some, but this is, I mean, still something that we need to look at. And of course, the uncertainties that I mentioned in regards to the benefits, that it's never quite clear, it's never that easy to make a clear business case.
Excellent. Well, thank you so much, Vianney, for a very fascinating presentation. If I can now please invite our next speaker, Magnus Reiden. Magnus is a professor at the Division of Energy Technology at Chalmers University of Technology in Göteborg, Sweden. He will present the development status for CO2 capture by chemical looping combustion, or CLC, and ongoing work within the CETP project A-Cloud. Please, everyone, I ask you to welcome Magnus.
Thanks a lot for the introduction, Alan. Can you see my slides?
We can indeed.
Perfect. Yes, I am then about to present this presentation with the title "Cutting the Cost of Biogenic CO2." Basically, I will present the following content. First, I will present this novel technology, chemical looping combustion, or as we use the abbreviation CLC. So I will make the case for why this is an interesting technology for CO2 capture. Then I will present this A-Cloud project, the basic pitch and activities which we do. This is one of these projects funded by CETP. And finally, I will present the status and outlook of chemical looping combustion globally and something about future outlook. So let me start then by trying to explain what chemical looping combustion is. Chemical looping combustion is a fluidized bed based technology. And a fluidized bed is something, as I show you here, I mean, it's a system, it's a reactor concept where we have a mix of gas and solids which are made to behave like a liquid, essentially. And that is done then by having the gas flow through the solid in an organized manner. And this is good because we achieve very good heat and mass transfer, good contact between gases and solids. And we can also pour this liquid and transport it between different reactor vessels. In chemical looping combustion, the starting point is something we call the fuel reactor, which is then a fluidized bed. And here we have the solid bed material would be something we call an oxygen carrier particle, abbreviated OC here. And the gas would be the fuel. And if we have a solid fuel, gas is generated by pyrolysis and gasification due to the temperature of the reactor. So let's use simple gases and oxygen carriers as an example. Fuel, in this case here, we use methane, and oxygen carrier would be hematite. That's simple iron oxide in this case. At suitable conditions, if we have a temperature of, say, 900 degrees, then the fuel will actually react with the oxygen carrier and form carbon dioxide and steam. And we will also then get a reduced oxygen carrier, in this case, magnetite. And this reduced oxygen carrier we can take to a second reactor vessel. This is also a fluidized bed, which we then fluidize with air. And at proper conditions, this means that the reduced oxygen carrier will be oxidized and we will get back our hematite. If we do this in a circular fashion, I mean, then the total reaction of this two-reactor system will be combustion of our fuel with pure oxygen. Heat is generated in the air reactor, while the fuel reactor is largely adiabatic. And what have we achieved? We have achieved that we are never mixing air and nitrogen with the flue gas which we generate. So when we just cool down the flue gas from the fuel reactor, we will obtain more or less pure CO2 simply by condensing the steam. And how can you build a reactor system like this? Something like this is the simplest way we can realize it. I mean, we have an air reactor, a fuel reactor, a cyclone, and two things we call a loop seal. We fill these reactor vessels, which are then fluidized beds, with our oxygen carrier particles, which is then in the form of sand-like particles, size perhaps something like 0.1 to 0.4 millimeter. The air reactor part we fluidize with high gas velocities, 2 to 5 meters per second. This means that we will actually blow these sand-like particles upwards. So this will act as what we in fluidization call a riser. These particles are then captured in the cyclone and transferred downwards in the system simply by gravity to the fuel reactor, where we are reducing it with our fuel. The loop seals in between the reactor paths, they work essentially as the water seal in a toilet. It prevents gas leakage between the two reactor parts. And everything here takes place at near atmospheric pressure and temperature in the range 800 to 1000 degrees. So these are about the same conditions as we have in an ordinary combustion facility. And there are many variants on this reactor system, but this is, I think, the simplest ones, and it makes, if you just will explain briefly how it works, I think it serves its purpose. So is this some kind of rocket science? Turns out it is not. This is very similar to our regular boiling technology, which is called circulating fluidized bed combustion. This is a common combustion technology used for solid fuels, especially biomass-based fuels, waste incineration, and also lignite. So only in Sweden, we have about 40 circulating fluidized bed boiler plants. So this is a common concept. And if we look, I mean, this has all the parts which the chemical looping combustion system needs. The furnace in the CFB boiler will be our air reactor, and the particle seal in the fuel reactor will be the fuel reactor, but of course it will need to be redesigned significantly. But in principle, the size, gas flows, heat transfer surfaces, and so on will be very much the same in a CFB boiler as in a CLC boiler. So why would we bother doing this? Yes, I mean, the reason why we want to do this is then to reduce the cost of CO2 capture. And this we could do very significantly with CLC compared to post-combustion. I mean, in theory, since we don't mix air and fuel, there is actually no energy penalty compared to conventional combustion for CO2 capture in theory. We can also achieve high capture rate. For absorption-based technologies, I mean, then you have some kind of diminishing returns when you reach very high capture rates. This does not occur for CLC, so here we can reach close to 100% capture rate. We can achieve low capex and small footprint. As we have seen, the size of the facility will be the same as our regular CFB boiler, and capex correlates largely with size. We don't need any harmful chemicals. The oxygen carrier we would want to use is probably a mineral ore concentrate like ilmenite, which is iron titanium ore, or some iron ore, or even some byproduct from metallurgical industries. And there are many studies trying to calculate CO2 capture costs and so on, and they usually end up somewhere in the range 20 to 25 euro per ton CO2, which is at least 50% cost reduction compared to air mines. So then let's move on to one of our current projects, which is the A-Cloud project, which is then a CETP project. We are 3 universities in this project. We are the coordinators, Chalmers in Gothenburg. Our colleagues are Technical University of Darmstadt and Åbo Academy University in Finland. We have technology providers, Sumitomo Foster Wheeler, which is the leading provider of CFB boilers in Europe, and Aleima, which is the leading provider of tubing materials for boilers and superheaters. We have a consult company, Chemin, in Germany, which works with corrosion and improved operation of boilers. We have end users, which are Stockholm Exergy and Skövde Energy, which are providers of district heating in Sweden. And then there are the Research Institute of Sweden, RISE, which is a research institute. And the pitch is that in Northern Europe, where we are based, in Sweden and Finland especially, we have very large biomass and industries, pulp and paper, forestry, and so on. So for us, these biomass and forestry wastes are very important to domestic fuels. And for Europe as a whole, also waste-derived fuels seems to be destined to increase in utilization in the coming years. And these fuels, for those of us who are interested in combustion and waste incineration, I mean, we know that these fuels, biomass, forestry waste, and waste-derived fuels are inhomogeneous and also have very problematic ash species. So they are actually more difficult fuels to handle than compared to fossil fuels such as coal and lignite, actually. And we believe that chemical open combustion would be an ideal conversion technology for this, due to several reasons. We not only have inherent CO2 capture, there is also this oxygen buffering capacity of the oxygen carrier. And also, and importantly, which is the main pitch of the project, is that we separate the heat transfer surfaces in boilers from the problematic ash from difficult fuels. So if we return to this figure, if we want to redesign our CFB boiler into a CLC boiler, we can notice that the red part here, the air reactor, and the black part, which is the convection section, these are the cost driving parts of a CFB boiler, because here we have our heat transfer surfaces. In a CLC boiler, these red and black parts will actually be free from the most problematic ash species we have in biomass and wastes, which is alkali related ashes. On the other hand, we will have much more concentrated ash in the brown part here, which is the fuel reactor. So this is something we want in the project to examine, verify, and make a viable design, with the ultimate goal then to improve the steam parameters of our boiler, which will allow us to increase electric efficiency for our facility, in addition then to capturing carbon dioxide. And what activities do we have specifically in this project? We will demonstrate in a 1 megawatt scale plant 2 relevant difficult fuels. It will be forestry waste and waste-derived fuel. We will also work on pilot scale. These are smaller reactors, and here we look specifically at fuel conversion pathways and this important ash chemistry. We also develop new analysis tools, especially for ash measurements, which means that we want to measure potassium species, especially online during operation. We also have then corrosion and material studies on both these pilots, the 1 megawatt and 10 kilowatt pilots. And this is then to examine if we can increase steam temperature for improved power generation. And also we have a work package about economic performance, environmental impact for key applications, and cost techno-economic analysis. And then we look at key applications, which is waste to energy and combined heat and power. And then for current status of CLC globally, this is not a new concept. It has been around for 20 years without reaching its full potential. Nevertheless, it has been demonstrated in more than 50 different pilot reactors all over the world. But we have about 80% of the experience here in Europe, actually. So we still have done a lot of development related to this concept. The largest demonstration plant which has been built is in China, which was taken into operation in 2024. It's in the 5 megawatt scale, which is not really not even a semi-commercial scale, I would say. However, most of the other 12,000 hours of operation is in lab scale, then 0.1 to 100 kilowatt scale. In Sweden, we have actually demonstrated the full chain logistics for oxygen carrier materials by operating more than 12 full-scale boilers with oxygen carriers. This has not involved CO2 capture, but we have demonstrated logistics and waste handling and so on. And this is then to improve performance of conventional boilers. We can easily achieve 100% fuel conversion and 100% CO2 capture with gases. With solids fuels, we have a more challenging situation, but good things to aim at is well above 90% of both these key metrics. And then there will need to be engineering to engineer the flue gas handling system of this. And my final slides then, take away specifically for this audience then, CCUS, chemical looping combustion, I believe represents a good midterm possibility if we want to significantly reduce cost for biogenic CO2 for utilization. However, it needs to be integrated with, it cannot be applied universally. It needs to be integrated with solid fuel combustion. This can be combined heat and power, waste incineration, or perhaps bark boilers on pulp mills. Key challenge is to take this to the next level, which is design and deployment of industrially relevant sized units. And this will really involve more active involvement of capable engineering companies. Up to this point, this is sort of hampered by, if we look at the situation here in Sweden, for example, and the Europe, most potential customers of CO2, they look at off-the-shelf technologies rather than trying to develop this technology into its full potential. So any help and ideas how to realize this final step from the audience would be very much appreciated. And that concludes my presentation. Thanks a lot for your attention.
Excellent. Thank you so much, Magnus. Your last slide of takeaways there actually stole two of the questions I was thinking about asking you. But I do have one here. How do you actually envision the CLC technology to best be integrated with CO2 utilization?
Yeah, mostly historically, we have looked a lot about CO2 storage within our research environment, just for climate benefits. But I mean, lately it has been started several projects then where actors who want to make electrofuels, for example, are making agreements with the kind of mid-sized district heating providers we have in Sweden, which utilize biomass. And then they are looking mostly at off-the-shelf technologies. But this, I think, if there is a true interest in making these electrofuels in this scale, which there are several, at least on paper, projects in Sweden at the moment, I mean, then I would say that this would be the best environment to try to take this technology to the next level. That's my hope.
Excellent. We have another question that's come through, and it's, what is the target capture cost per tonne of CO2 in the CLC project?
Yes, I think there are, of course, over the years, there have been many techno-economic analyses for this. Most of them ends up somewhere, I would say, in the span 15 to 40 euro per ton CO2. That's only for the capture step. And of course, this depends on scale. Those who look specifically at biomass, they tend to end up slightly higher than coal. I think it's very difficult to do this kind of studies. I would rather say that if we look at what we need to build and compare it to the post-combustion case, and the kind of energy penalty which we will achieve, then I'm pretty sure that we would end up much better. So I think I rather say that the cost target which we look at, I think that having this 50% reduction in cost compared to air mines for a similar plant, I think is a target I'm more comfortable with compared to saying this 20 euro per ton capture cost.
Excellent. And one last question, which possibly a very quick one. Who would be your dream partner? Just on that last takeaway slide, you were talking about the need for big engineering input. So who, for example, is your dream collaborator to actually move the project forward?
Yeah, I mean, we have our dream collaborator in the A-Cloud project, which is Sumitomo Foster Wheeler. We just want our dream collaborator to but they also have other capture technologies in their project portfolio, of course. So I guess we need to convince them that this is the correct way forward.
Excellent. Thank you so much, Magnus.
Yes.
I will now move to our next speaker, but before I do, one quick prompt for everyone. We will have time for Q&A at the end if you'd like to put your questions into the chat addressing which speaker you'd like it to go to. So last call for those questions, get them in now. But if I could, please, I want to introduce our last but by no means least presenter on our webinar today, and that is Bianca Sekliner. Bianca works as a Sustainable Technologies and Decarbonisation Manager at RHI Magnesita. She is committed to driving the transition from hard-to-abate industries to climate neutrality. Today, Bianca will be presenting the RHI Magnesita's ongoing CCUS project and explain their main challenges. Please give her a warm welcome. Over to you.
Thank you, Alan, for the introduction. I'm happy to share with you the decarbonisation strategy of RHI Magnesita through CCUS technologies. But before I go into the topic itself, I want to give you a short overview of the company. So RHI Magnesita is the global leader in refractories. We do produce our refractories all over the world in 65 production sites. We are also running 12 recycling facilities and 5 R&D centers. Last year, the company has generated a revenue of 3.5 billion euro with over 22,000 employees. We have over 1,700 active patents running, and we do invest a lot of money into R&D and technical marketing. For those of you who have not come across refractories so far, it can be said that they are really necessary for our modern life as we know it. There would not be any modern building, no transportation system, energy production, communication system, or whatsoever without refractories, because all of these things require materials that are produced at really high temperatures. So concrete, copper, steel, glass, aluminum, they're all manufactured at over 1,000 degrees Celsius, and these manufacturing processes require refractories. How do they look like? On the next slide, I have a few examples. They are either produced in different shapes of bricks, or they are sent to our customers as monolithics and then applied there in their vessels, or as precastables or functional products. The industries that we're serving are mainly the iron and steel industry, but also cement and lime, non-ferrous metals, also the waste incineration and glass production. They all need our products. And here on this slide, I want to show you why exactly refractories fall under the hard-to-abate definition, because mainly, hard-to-abate, for example, the cement industry, but also we as a refractory producer fall under this definition, because compared to other refractory producers, we are highly backward integrated, which means that we produce a majority of our raw materials by ourselves. You see on the left hand side on the top the depiction of the raw material production. So we mine dolomite and magnesite in open pit mines. And then this material runs through a long rotary kiln and is calcinated at 1,800 degrees. And this very process impacts us with the CO2 emissions. The scope 1 process and fuel emissions that derive from this raw material production imposes us with great challenges to decarbonize our operations. Yeah, so the raw material produced is then either pressed into bricks or sent unshaped to our products. Then they are used and ideally recycled and put back into the production process. And on the top, it is shown in more detail this calcination process, where if you burn a ton of MgCO3 at 1,800 degrees, you only get half a ton of MgO, which is the raw material for the refractory production, and half a ton of geogenic CO2 emissions. On top of that, there are also then the fuel emissions, but basically these geogenic CO2 emissions are those hard to abate, which make us hard to abate. Of these 65 production sites, less than 10% cause 80% of our scope 1 and 2 emissions, which can be seen on this graph, where you see all over the globe, like in Brazil, in North America, in Austria, in Turkey, and China, the production sites cause these CO2 emissions. And this is also why we focus our CCUS technologies on the raw material sites. Basically, RHI Magnesita wants to lead the industry, not in terms of also products and systems, but also in terms of decarbonizing our operations as fast as sustainably possible. We do invest a lot of money in projects like this mineralization project, which I will discuss in more detail in the next slides. We are continuously increasing our recycling rate and to avoid CO2 emissions in the first place. We are very transparent with our customers. We show our carbon footprint on all our technical data sheets of our products, so the customers are aware of our carbon footprint. And we work very closely together with industry partners who have the same challenges as we do to develop new renewable energy solutions and also hydrogen energy network. In our yearly report, we have already published our 2030 sustainability goals. And here it has to be said that sustainability is not only CO2, but also energy efficiency. Safety is a very important aspect of our sustainability journey, and also sustainable supply chains. On the next slide, you can see an overview of the options that we as a company have to reduce our carbon footprint. Firstly, we want to avoid CO2 emissions as much as possible, but based on the raw material that we have that I showed in the first slides, we cannot avoid them totally. So we have them intrinsic in our raw materials, but by increasing the recycling rate, we want to reduce the CO2 as much as possible. We are also investigating to use non-carbonate-based raw materials. We are trying to electrify all the processes that are running below 1,000 degrees Celsius. And we are trying to switch to fuels that have a lower carbon footprint, like biofuels or green hydrogen. The rest of the CO2 that cannot be avoided by these measures, this has to be has to be captured, utilized, or stored. And this can be seen on the right-hand side of this graph. So we are looking into storage options. For example, in China, we have an FFG project running there. It's called Abate-C. And we've investigated also to probably utilize the CO2, as shown in, I think, one of the first presentations of this webinar. But here we came to the conclusion that the raw material sites that we have are so far off the infrastructure to have the necessary electricity that we cannot utilize the captured CO2 directly there. This is also why it says in the headline that infrastructure is key for all of these CCUS technologies. And this is also why we focus very much on this mineralization option to decarbonize the raw material sites. On CCUS, we have two FFG funded projects running. One is this Abate C, where we are together with a Chinese university and the Mutan University of Leoben investigating options in the Anhui province, whether it would be possible to store the CO2 of this one Chinese production site there. And we have the CCU Upscale project, where I go into detail now in the following slides, also FFG funded and several partners working together with us. One very important to mention is MCI, Mineral Carbonation International, who brings this mineralization technology to this whole project. The general process itself is set up like this, that we can take the flue gas as is from our rotary kiln with a percentage of 15% CO2 and let it react in a reactor together with a feedstock, which is in our case serpentinite, which is being milled and pre-treated, heat-treated, to then react with the CO2 from the flue gas. And we do get two output products. One is a siliceous product, and the other one is a precipitated magnesium carbonate. I will go into detail into the feedstock, the product, and then in the in and out mass balance. But first of all, I'll start off with the feedstock. We decided to go to with serpentinite because it's available in large quantities and abundant worldwide. What's tricky so far that the current applications of serpentinite have never made it necessary to check the chemical and mineralogical characterization. So this is something where we put a lot of effort into, because this mineralogical composition affects the total process very much. So the abatement potential is dependent on this feedstock, the product specifications in the end as well. So we take a really close look on taking the right quality from these serpentinite pit mines. The products that are then coming out after this mineralization process are, on the one hand, silica-rich powder. It's very fine, and an MgO-C product. And we do see here multiple applications in the building sector, as we could use it as refractory ceramics, but also see application in plaster and cardboards, fertilizers, or the paper production. What's compared to a mere CCS option, where we would only store it and have only like a cash out thing to do, here we see the real benefit that we do see new business opportunities where we could sell these new industrial minerals to potential customers. And apart from this aspect, it's also very promising that this a very energy efficient process. It runs at low temperatures and pressures. We do not need any further additional chemicals for this reaction process, and we can take the CO2 directly from the off gas from our rotary kiln. So more detail on the products. There are two more slides. One of the siliceous one for you to understand it a bit better. It's really fine. So 90% are below 25 microns. We have a independent lab testing the reactivities and activities of this material. So to check whether it would be suitable, for example, for the cement industry as a supplementary clinker material, and here the results are really promising. So it seems to be really reactive. What is still outstanding are the I think durability tests. Here we're still waiting on the results, but overall we are also in discussion also with potential customers, and it looks overall really promising, so that this can substitute clinker in the future. It's a very, I said already, fine material. Amorphous content is about 50%, and this would be the siliceous product. The other one is the precipitated magnesium carbonate, also very fine. 90% are even below 18 microns. Here it has to be stressed out that it's really white, fine powder, and it comes in different mineralogical compositions. And there are also several applications where we're looking into them, which will be seen on the next slide. On both products, it can be said that it comes out as a wet filter cake, and if it can be used as a filter cake, the carbon footprint is rather low. If we do have to dry the product, this carbon footprint would go up again. But basically, if our customers could use the wet filter cake for their production sites, it is a really low carbon footprint mineral product. So on the feedstock, the products, I've given you some details here, the key developments. So basically the technology is running in a pilot version since 2016 in Australia. The next scale up that could save 1,000 tons of CO2 per year is currently under commissioning, also in Australia. And this is also the basis for our planning of the first commercial pilot in Europe in one of our Austrian sites, where we want to capture 50,000 tons of CO2 per year. And this project, the CCU Upscale, has also won the Net Zero Industries Award at the COP29 last year, and has this funding aspect as well. So these are the key developments. So we are really proud that we are working on the first commercial pilot here on this mineralization technology. One last slide before I come to the end is about the in-out mass balance, to give you an overview. So if we want to capture 50,000 tons of CO2 of the flue gas, we would then mineralize it together with a serpentinite and get 2/3 would be the siliceous product, where we could find applications, as I said, in the cement industry to reduce the clinker rate if we can increase the usage up to 20%. And this is also, this looks very promising to be suitable for this industry. And the precipitated magnesium carbonate has several applications. Some of them are already kind of accepted for EU ETS counting. So for construction products, this counts as permanently bound.
Am I the only person who cannot hear Bianca speaking?
I haven't heard any feedback.
We can hear Bianca speaking.
So maybe it's only Ellen.
Yes, could be a local thing.
Okay. So 2/3 would be siliceous product for the cement industry, and 1/3 would be precipitated magnesium carbonate, possible for the construction product, but also for minerals, fillers, for different uses. And here it's really important to, I think I have to enter Ellen. Important to say that currently this does not count yet as permanently bound, but we are very much putting a focus on this, that some of these fillers, for example, in detergents, should be added to the appendix of this EU directive, because it's also kind of, it won't enter the atmosphere in the future. So there are several options to apply these minerals, and there's a lot of work still to be done, and also to kind of prove that these applications then are permanently bound. We could also use this material in our own production process and substitute primary magnesite, which would enhance this circular concept of ours. And to sum it up, we see this mineralization technology really as an option to turn CO2 into valuable materials. To have, we have new fine-grained low-carbon products like the siliceous and the precipitated magnesium carbonate. We see various applications and are in discussion with several potential customers that could use these minerals that have a reduced carbon footprint, and we are establishing a lot of new cooperations to get this technology flying. And if you're interested in more facts and figures, I've added here 2 QR codes and also the sites. We have a separate site for the CCU hub that explains a bit more in detail the mineralization technology, and also a QR code on magnesite and why refractories are so important for our green transition in Europe and worldwide. So, and I'm open to questions from your end.
Excellent. Thank you so much for that, Bianca. I have a question to lead off with here, please. But before I do, this is your last call to the audience. If you'd like to put in questions for any of our speakers, we do have that opportunity, and they have all rejoined the call if you'd like to put them into the chat. But please identify who you'd like that question to be addressed to. But question for you, please, Bianca. Could you elaborate on why RHI Magnesita has prioritised mineral carbonation in its decarbonisation strategy compared to the other available technologies?
Sure. As mentioned also in the other presentations before, green hydrogen is necessary to get rid of the fuel emissions, and also for many utilization technologies. And our sites are all in remote valleys. Yeah, so we don't assume that before 2040 we would be part of any start net for green hydrogen pipelines or even CO2 pipelines. So this will come, I think, in a later stage. So we're looking for options where we could decarbonize our production sites before this time, and being more independent of these infrastructural topics, where we depended on whether we have access to green hydrogen or CO2 pipelines, and said with this mineralization option, we could do it ourselves before 2035.
Excellent, thank you. A question that's come from our chat. Is it solid or aqueous CO2 mineralization? And the question goes on to say, wouldn't the high T&P, temperature and pressure, I imagine, used for the reaction compromise the purpose of CO2 utilization?
I'm not sure whether I understood it correctly. So if it's, we use water in the reactor, so it's in a solution, yeah? Could you repeat maybe the question, because I cannot read it?
Oh, sorry. It says, is it solid or aqueous CO2 mineralization? Is the first question.
It's then it's bound in a mineral, so it's CO2 is then, but it's how do I say this correctly? It's the phases that does it give you the answer in the mineralogical phases? So it's MgCO3 with water, but it's solid, yeah. It's these stable phases, but it's a mineral.
Excellent. Now,
so it's natriumite, hydrogen, magnesite. Do you see those options? It's a mixture of those, dependent on the feedstock, but it's a mineral.
Excellent. Now, if there is a further question needed on that from Kun Tian, please put it in the chat. The other question I have here for you, just my screen has just gone away, is how important are partnerships? It's been a big theme, obviously. We're in partnership with the CETP for this presentation, but how important are partnerships or regulatory frameworks for RHIM in reaching its decarbonisation goals?
They're highly important, because we need for these two products, we need customers and industries that are interested in the product itself, and we need to work together with them to understand whether the application, the specifications are suitable for their applications. So the collaboration with them, but also the legal framework needs to be reliant, so that we know that this really counts as how do you say, as a EU ETS, in German it says, es wird angerechnet. What's the English version for that?
I do not know.
We get the certificates then. So we get that it counts that we decreased our CO2, that we didn't emit it. Yeah. And therefore the legal frameworks are also really essential. So we're working on all those ends, on cooperations with customers, with other industry partners, but also on explaining the different applications, and to keep it open, to not kind of ban a certain application, because then there is no option to further research and develop, and maybe then develop something that would be beneficial for the atmosphere just by cancelling out some options in the first place.
Excellent. And we do have one question there also from our Q&A page, asking if you would mind commenting on decreasing magnesite mining versus increasing serpentinite mining.
I think we've heard this question before, but this is in terms of the circular concept in our production site. We would then reduce the magnesite mining because we would have the magnesite out of this mineralization process. Yeah, and the serpentinite mines, they are anyway already running. It's usually it's a byproduct of another material, and now we are seeing an option to use the serpentinite for our needs.
Excellent.
Does this
Thank you.
answer the question?
I think it addresses it well from my perspective. If it doesn't, please let the chat let us know. I don't have any other questions. I think we've done a marvellous job, because we've managed to stay on time almost to the minute with every speaker, and managed to answer every question that's been asked of every speaker. So it falls to me to hand over, please, to Urban Piker, to actually make a small closing statement before I just do some small housekeeping at the end. So Urban, if you wouldn't mind, and thank you again, Bianca.
Yes.
Sure. Thanks, Alan, and thanks for the opportunity for closing this webinar. Allow me an attempt for a personal wrap-up of today's session. So our discussion has once again underlined how central CCUS technologies are in reaching climate neutrality. And as we've heard, carbon capture and utilization are not optional. They are part of very credible net zero pathways. And importantly, CCU should not be seen merely as a temporary storage solution, but as a lever for creating lasting value and transformation in industrial systems. Or as Peter has had it in the title of his paper, CCU, it's more than hiding CO2 for some time. So I think this really gave me some further perspective on how to look at CCU. And the science is there, and obviously the patents are available as well in many cases. But at the same time, we must acknowledge that advanced capture technologies are still evolving, and bringing them to market will still take time and effort. So that's vital to invest in focused research and innovation. This is certainly a process that is still ongoing and still needs to be further supported. That's important not only to reduce costs, but to ensure at the same time deployment at scale across the hard-to-abate sectors. And achieving this will require us to take a very comprehensive view of the entire value chain. I think that has been shown in a very good way in the project examples that we have seen. So from capture to reuse to storage. And I think it's important to recognize the critical role of hydrogen and industrial symbiosis if we want to go further ahead. As usual, it was very inspiring to see concrete examples of international cooperation, and including advancements in iron and steel, chemical looping, combustion using biomass, and as we've seen just at the end, CO2 mineralization. These are all promising routes for both carbon management and circularity. And at that point, I would like to thank all the speakers for your incredible work and for your time and for your input in today's webinar. Thanks for that. And we hope that today's session has sparked ideas and further strengthened trust in the potential of the presented technologies. As I said at the beginning, the road to net zero is complex. Collaboration and shared knowledge, like we saw today, will be essential to make it achievable. So thanks once again, and we look forward to continuing this important journey with you. Until next time, and I don't know if you wanted to say something about that, Alan. If not, I'll take the opportunity. Next topic will be on financing. So if you're interested in that, that could be an opportunity to join us again on the 5th of June. We will host a webinar together with the Alliance for Industry Decarbonisation, and the topic will be financing the green shift, unlocking climate capital for emerging markets. So some advertisement here at the end from my side, and thank you for joining, and goodbye for now from my side. And by that, back to you, Alan.
Thank you, Urban. Yes, you've saved me the trouble of doing the pitch for our next upcoming event. If you want to get access to register for that event, please go to our website. You'll see in the chat that we have links for our website and the events page. We also have a link for LinkedIn where you can actually follow and see what we're presenting next. And if you scroll up a little bit further, you will actually see a survey that we would invite all of our audience to fill in, to give us feedback on what you'd like to see in future topics, how well these webinars go, and how you've delivered value for them, from them, to actually help you in your own challenges and goals. But on that, I will echo the thanks to all of our speakers, to Peter, to Hannele, Jorge, Leonie, Magnus, and Bianca. On behalf of the entire Net Zero Industries team, thank you so much. I'd also like to say a special thanks to the team behind the scenes. The Secretariat team for Net Zero Industries mission put an enormous effort into making sure that these events run smoothly, that we manage to get high quality speakers, and that we actually can present for you some absolutely valuable and interesting information. We will be publishing this on our YouTube channel and on our website very soon, and the presentations in PDF format will also be published on our website. With all of that, thank you all for attending. Thank you all for your interest. Thank you again to our speakers. Thank you, Urban. And here it's getting quite late in Australia, so good night, good day, and we will hope to see you all next time. Thank you very much.
Thank you. Bye.
Thanks a lot. Bye.